So good morning students. Yesterday we have derived the constitutive equation. Now we will try to express those constitutive equations in Cartesian form and the use of this constitutive equation as Navier-Stokes equation. So this is our main intention today. So first this is the constitutive equation which we had from our previous lecture, and if the fluid is incompressible, so then from continuity equation, this is the continuity equation for incompressible fluid. So if the fluid is incompressible, that rho, this is the density, this becomes a constant, and so the rate of change of a constant will be 0. So ultimately from the constitutive equation we will get that the divergence of the velocity vector is 0. So this is the case. So we substitute that divergence of velocity vector as 0 in this part. Okay. So after substituting that value, we are getting, this is the equation. Okay. So this is the stress, and it has two parts. First part is the pressure part and the second part is the viscous part. And that viscous part is denoted by tau ij. And if you see in the pressure part, there is a negative sign. This negative sign indicates the direction of the pressure. Okay, generally pressure acts along the inward direction. Now we try to express those viscous part in Cartesian form. So for that what we do, we replace our in tau ij, we replace I and j by xx. So tau xx will be twice mu dxx. Now what is the expression of dxx? So this is the your dij definition. So if you replace ij by xx or 1 1, generally 1 represents for x direction, 2 represents for y direction. Okay, so in your right hand side it will be half of del v1 del x1 plus del v1 del x1. Okay, so v1 is the first velocity component, that is u, and x1 is the first displacement component, that is x. So similarly we are getting del u del x. So ultimately the value of dxx is equal to del u del x. So that we have obtained tau xx as twice mu dxx. This is twice mu del u del x. Similarly tau xy, this will be twice mu dxy. Now for dxy, what you do, you replace your x I by x and j by y. So you will get this expression, that is mu times del u del y plus del v del x, and that will also be equal to tau yx. You can verify it. Similarly your tau xz will be mu times del u del z plus del w del x, and that will be your tau zx. Tau yz will be mu times del v del z plus del w del y, and tau yy will be twice mu del v del y, and tau zz will be twice mu del w del z. You can verify all this part in your home. So after knowing this tau xx, tau yx, yxz, etc., etc., now we will go to our conservation law of linear momentum equation. So these are the three equations based on the conservation law of linear moment. Now what we do, we replace this tau xx, tau yx and tau zx from the previous expression. So this is the expression of tau xx, that is del del x of twice mu del u del x. This is our tau xx. This is our tau yx, and this is our tau zx. Okay, so now we divide both the side by rho, so we are getting the expression. Now you see here 2 times is there. What is the term? 2 times of second order derivative of u with respect to x. So from that 2 terms we are writing one term. Now we are taking this term, that is a del 2u del y square, and from the last part we are taking the third one, that is del 2u del z square. Okay. Now what are those remaining terms? Here one term is there, we have written. Here one term is there. What is that term? Del 2v del x del y. Okay, we have written. And here one term is there, that is del 2w del x del z. From each of this term, the operator del x is common. So what is the remaining one? Del u del x plus del v del y plus del w del z. and this bracketed part, this is nothing but your divergence of velocity vector, and for incompressible fluid the divergence of velocity vector is 0, so ultimately these three terms gives 0. Okay, so that's why this term is cancelled, okay, because of using the continuity equation. So now what we are getting, this is same as previous, same as previous, same as previous. Now from this term, if you take us common, you are getting the expression as that this is nothing but your Laplacian, that is the delta square or nebula square. So this equation is the simplified form of your equation A after substituting the values of tau xx, tau yx and tau zx. Now what we do, in the same fashion, if we proceed for B and C, we are getting the expression as this and this. So these are the simplified form of your B and C. This is your star. The star comes from the equation along x-axis. This is double star. This comes from the equation along y-axis, and this is triple star. So combining this three equation, that is star, double star and triple star, in vector form, we can write down one simple equation, that ddt of q bar equal to b bar minus 1 by rho del p plus mu by rho del square. Where what is your q bar? Q bar, it has expression like this. This is the velocity of the fluid at any time t at a point p. B bar, this is the body force per unit mass, and it has three components. Del, this is our nebula, and del square, we have this expression. So this equation, this simplified equation in vector form, this is known as the Navier stokes equation.